Dr. Ayman, the procedure, I'm going to start first to introduce you, and then, okay.
We are live.
Okay. Welcome to the University of Dubai College of Engineering and Information Technology series of seminars in collaboration with the IEEE UAE sections. And this seminar actually is going to be associated with IEEE UAE Engineering for Medicine and Biology Society chapter, Computer Society chapter, Robotics and Control Society chapter, and Youth Young Professional chapters. We are honored and glad to have Professor Ayman El-Baz from University of Louisville, and he is actually the chair of the bioengineering at the university. Also, we have in the panel Dr. Isa Bastaki, President of University of Dubai, Professor Hussein Al-Ahmed, the Dean of the College of Engineering and Information Technology, and Engineer Ayman from the Electrical Engineering Department. The procedure of the seminar, Professor Ayman will start and then will be followed by questions from the panels, and then we'll take the questions from the audience. The title of the seminar is Big Data for Smart and Connected Health, and I leave the floor to Professor Ayman. Please, Professor.
Okay, thank you so much, Dr. Wasik, and also I'd like to thank Dr. Isa and Dr. Hussein for giving me the opportunity to share my research with the audience from United Arab Emirates, especially from University of Dubai. And, the main focus right now of my lab and what we are trying to do is called precision medicine or personalized medicine. And when we go to in this direction, everyone aware of this is when we have patient group suffer from certain disease, especially right now, for example, for corona. This is one of the projects that we have. The response for coronavirus is different from patient to patient. The same, especially for cancer. And right now, when we start, for example, chemotherapy and radiotherapy, the response to the treatment different from patient to patient. So we started, so the current technique right now, they try to make a general medicine or a general protocol for all patients. And the main problem, the response for this type of treatment is not good. So for personalized medicine, what we'll try, we need to now to use more markers or more inputs. So in case if we can identify a specific treatment for a certain patient, in this case, we can enhance the outcome, and when we mean the outcome in terms of health, also in terms of cost, because both of them is very good, is important. For example, when I talk about chemotherapy, it is very expensive. So if I decided at the beginning the chemotherapy is not the best solution for this patient, this is mean I reduce money, and the second also I avoid this patient from the consequences of chemotherapy. So this is the main idea, and I started to collaborate right now with Cleveland Clinic at Abu Dhabi and University of Louisville and Mansoura University to collect some data, especially to start to see the response in terms of breast cancer and bladder cancer. This is the two types of cancer we focus on them, in addition to the autism, the one that I will present today. So right now, when we started to talk about big data, maybe you can have one source, but the size of it is very big. Or big data also it can cover, you have many sources of data. For example, when I talk about field of medicine, I have clinical marker like blood test, urine test. Also, we can have imaging marker come from CT, X-ray, MRI. We can give right now genome data. And right now, most of the countries started to start a project for genome bank because we know we can, based on genomic analysis, we can predict the risk for a certain disease in a certain area or in a certain country. So also family history. The family history is very important. We start to now, when someone come to talk with him, I can ask, did anyone in your family has this type of cancer? Are you a smoker? What? All this is information we need to know. In addition, for example, and this is very important, pathology images. We get histology images. So right now, this is the current focus of my lab, to use all this type, but even not like this. In a smart city like Dubai, we have some environmental sensor. So I can use, in addition to what I mentioned, some information about the area. If you live in areas that has a lot of pollution, different than if you live in a clean area. For example, if someone has lung nodule or lung tumor, if he live close in areas that has a lot of pollution, high probability this is benign. This is come from the air. But if someone live in very clean area and I see tumor inside his lung, this is, I have to investigate more because this is high probability to be malignant. So right now this is what we plan in, especially now in Louisville and El-Alamein, our new branch, to get data from hospital. For sure, we get data from university. We can get, this is the most important. This is why we start to talk about smart city, to take some data about the pollution in this city by putting a lot of sensor in that cover the city. And I think Dubai, one of them. And right now I hear from President of Egypt that El-Alamein city, they will try to also to make it similar to Dubai by putting some smart sensor in every place. Demographic data. This is very important to get information about each subject in terms of gender, in terms of age, in terms of race, in terms of family history. And we try to include all this is under the umbrella of, we call it big data. So this is the definition of big data that I using during my presentation. So we have all this type of data: imaging, clinical, genome, pathology, and environmental. So why big data is important? As I told you, big data is become very difficult and no one can take care of it alone. So if you talk about physician, and when I go to there, the physician can read imaging, the physician can read genome, the physician can read urine test, but it is very difficult to combine all of them. This is why right now the teams that they work in big data, not only physician, we need IT team because the data is huge. For example, right now I work in a project lung cancer. I rent from Amazon around 100 tera to just for one project, because even the data that I am using is huge data. When we work with NIH, the genome data is huge data. So NIH in US, even right now, buy some space from Amazon Cloud to store this data. So we need some people from IT to help us to store this data and also give us a way to access data in fast way. So this is why we need IT. We need also we need some people who, this is huge data. So you need some people who can develop fast computational approaches. So this is another thing which is very important that we have to take into account. Scientists, for example, when we have a problem, physician usually knows a problem, but in order to find a solution for it, it must come from the scientist. This is why we work with the people who have basic science foundation from pharmacology, from biochemistry, from molecular biology, because this is the people who start to put the hypothesis. From the hypothesis, we start the engineering, start to develop an approach to validate, or this is hypothesis. So this is what we need. In addition, we need commercialization people, because if I am developing a technology, I need, as we discussed before this talk with Dr. Isa, yes, when you have something good, you have to teach the community. So commercialization people, who's the people who can market the final product. And to make it access, because everyone knows that the world become as a small city. So right now we can make it access to everyone through cloud system. That's why now when I develop technology, the people from United Arab can access, from Egypt they can access, from Europe can access. How we can do this? By building in cloud system. So as when Dr. Isa visit our lab, we have many projects in our lab. So we have brain, and the brain we are focusing autism, dyslexia, and Alzheimer. We also work on heart, lung cancer, prostate cancer, kidney. In kidney, we work on right now on kidney cancer and acute renal rejection. And we have a spinal cord center. And the last one was diabetics. In addition to this, we started this year a lot of another 5 or 6 projects in collaboration with Abu Dhabi and the Cleveland Clinic at United Arab Emirates and the Mansoura University, one in COVID-19, one in bladder cancer, one in breast cancer, and one in renal cancer. So this is when I started to do again, and this is when I go to Egypt and we started our branch. The old fashion of to do research is that everyone can do the research by his own or her own. But really, this is not the current environment to do good research, high quality of research. And also, this research must return money. So before I present any project, you see that in any project, as we mentioned, we have commercialization team. This is people has MBA, Master of Business Administration. We have the software engineer. We have the clinical people and scientists. This is the team in each project, and we work as a team. And the success will be the success for the whole team. If the team fail, this is the fail for whole team. So this is the first one. This is, for example, we talk about lung cancer. And the lung cancer, one of the most difficult cancer to make diagnosis for it. Why? Because to reach the lung is not easy. There is 2 ways to reach the lung: by biopsy, and the biopsy can give good result if the tumor close to large airways, because in this case you can reach it. But if it is far away, like this, very difficult to reach. So the second way is to use needle biopsy, and the needle biopsy from outside, you inject the needle to the chest like fishing, and you start to, after you put the needle, you put the patient in the scanner and to check where is the needle. If the needle appear inside the tumor, you take some sample. If it didn't appear inside the tumor, you have to take the needle again back and push it. You can't repeat this more than 10 times, because as you repeat more, you cause a lot of bleeding, and this is bleeding can hurt the patient. What we did here, and we started to use CT scan, and the CT scan we can take 2 CT scan, the period between them 6 months, and we can measure the growth rate, how the growth of the tumor, because benign tumor usually the growth rate is 0 or very little, but malignant tumor, no, it can double in size in 2 years. So in this case, in this is technology, within 6 months, I can make initial assessment to the tumor to say this is tumor is malignant or benign. And by the way, this was my first grant in my career. I got it in 2006 when I started as assistant professor in bioengineering. The second grant, Johnson & Johnson come and they say to us, and this is the company, and this company approaches by Jessica from commercialization team, contact Johnson & Johnson, tell them what we are doing at University of Louisville. Then they say, yes, we are interested in this technology. They ask 6 months is too much. Can you shrink this period? I say yes, we can make it 3 months if we add a third component to the system that we collect what is called contrast enhancement CT. So we use like dye. This is dye we inject, and if it is malignant tumor, this is dye will appear so fast in the malignant tumor. If it is benign, it will take a little bit time. So Johnson & Johnson say this is very good, but they say, Ayman, this is not enough. We need now to make it in 1 day. This is why I start to collaborate with 2 more teams from biochemistry and from chemical engineer. So, and this is based on the hypothesis, when someone has cancer, is the breath, the compound of the air come from his mouth, it is changed. And I started to use we did a microchip that this is microchip around $5. I take the patient push the air inside this chip, and we make analysis to it, and we measure the carbon component inside this is the air, and I add this is breath marker to what I have from imaging, and we able to reach accuracy around 95% from the first visit. And this was the challenge. And right now, this is technology is licensed by Johnson & Johnson. So now to see, we start with a small idea, and with time it starts to grow until it fit the market. So I start to work on this project in 2001. We reached this is high accuracy in 2018. What this is mean, and this is what I keep convinced the Egyptian university, that when we have do a master, we don't need a topic per student. We need a topic and the student to make part, then second the student to continue, third student to continue. In this case, you can end with a good product. Because for example, even this is started with me, but it is completed by my student. This is one phase. After we did this, the doctor say, Ayman, this is very good, but we have another problem. After we make a diagnosis to the tumor, and if this tumor is malignant, the patient will go to chemotherapy. A chemotherapy is another scenario. So now we need the chemotherapy to treat the patient, not to kill the patient. So they need to develop another technology to tell the doctor, you have to stop now, because if you keep doing chemotherapy, the chemotherapy will make lung failure, and the patient will die from chemotherapy, not from the cancer. And based on this, we develop this technology that
Is it frozen?
Yes.
Dr. Ayman, I think you're frozen.
I think his computer might have frozen, Doctor.
Yeah, but he has to know it. He doesn't know it maybe. Dr. Ayman?
Iman, can you call him on the phone, probably?
I will call him.
Okay.
I will call him.
Oh, he's coming to come back. I think he left.
Yeah, I'll call him anyway.
دكتور حسن نشاش كيف حالك ابو احمد؟
I think he cannot. Yeah, okay.
السلام عليكم، حيا الله بمروان.
هلا ابو احمد، شو اخبارك؟ ان شاء الله بخير؟
كيف حالكم؟
الحمد لله. انا شفتك جالس برا قد ما
الله يحفظك.
يمكن تجي برا، انت تدخل داخل معنا. ابو احمد؟
لا انا موجود معاكم اكيد.
لا اول كنت برا، فانا يوم شفت اسمك قلت لهم دخلوه داخل عنا. جزاك الله خير دكتور.
الله يسلمك. شكرا مروان.
بس شيقه المحاضره، شيقه ما شاء الله.
الحمد لله.
ممكن تدخل مره اخرى؟
متى اجتماعنا القادم من اجل البي ام اي؟
لا بس ادخل مره.
فاكر كنا
مال ساينتست؟
صراحه
الشهر الماضي يعني ما حد قال شيء فما اجتمعت. اذا في حد يطلب الشهر ان شاء الله يمكن نجتمع، بس خلينا نشوف بعد.
خلينا نشوف لايف.
اذا شوف الناس يبون انا اجيس النبض انا شويه.
اوكي.
انا صراحه ابغى اخوي يدخل في هذا، لو ادري من اول كنت اقول حق اخوي يدخل، مهتم بهالاشياء هاي.
شكرا يا دكتور، مع السلامة.
رجع الدكتور، رجع خلاص.
رجع دكتور أيمن. Okay. I don't know, for some reason the system
Kick me out.
took him out of.
The reason that they kick me out.
Yeah.
Just
Can you open your video, Dr.
I
Ayman?
will open it right now.
انا you weren't kicked off. I think في كان مشكله في النتورك عندكم.
ممكن. I just know. Yes. This is the one. Did you see my screen, Dr. Isa? Or not?
No.
Not yet.
No.
Abdullah?
Your video is not on.
I will try. Did you see Dr. Isa now?
Yes. Yeah. That's fine.
I'm so sorry.
Yeah, it's okay. So continue,
Okay,
Professor.
so what we mentioned here, we develop a technology now to tell the physician when they can stop based on measuring the ventilation and how elastic the tissue, and we can give a matrix after we did this after 4 sessions of the chemotherapy. After each the patient do 4 sessions chemotherapy, we make 4-dimensional CT scan, and we try to use it to measure how elastic the tissue and the ventilation. And by the way, this is technology right now, we use it for COVID-19 to tell who has to go to, who has to put him under ventilation based on measuring the ventilation and how elastic the tissue. So, and this is one of the current projects right now in the lab for COVID-19. For prostate cancer, I mentioned this. I did this is because in 2008, my advisor from University of Auckland, I touch with him every week. As soon as I send him an email, within half an hour I get a response. Then he disappeared for 6 months, and I think there is some problem. Maybe he's unhappy from me or something. Then when I met him in a conference, the first question I asked to him, where are you? He started to tell me what he suffered. He told me he still feels that he get tired from his work. That again, his regime that he's doing every day, he didn't change, but he started to feel that he get very tired when he started to give a lecture or something. Then he go to the doctor say, this is maybe prostate cancer, and they asked for BCA. When this is BCA is a clinic blood markers. When he did it, it was normal. Then after 3 months, he go to him again and they say, I feel I didn't feel well. Then they did biopsy for him. The biopsy come negative. Then after 3 months again, he go to the doctor. I say, I feel I didn't feel well. So the doctor make another biopsy for him, and the biopsy this time confirmed it is prostate cancer. And he tell him, okay, the good news that the prostate cancer is still local. This is mean the treatment from the prostate cancer will be 100%. But he shared with me the experience that the biopsy is very painful. Second, he did it 2 times to able to get with this result. So we started to discuss how we can do something comprehensive and non-invasive. And here we use diffusion-weighted MRI, and the diffusion-weighted MRI is measures the percentage of the blood inside the prostate, and from it we can detect if this malignant tumor or benign, because the theory here or the hypothesis that the malignant tumor usually will feed it by blood supply. He get a lot of blood to grow fast, and we got accuracy here is around 99%. And we just got a grant right now from Egyptian government to start to use this idea to personalize medicine by integrating patient questionnaire. We will ask the patient 10 questions, and we'll ask the patient to tell us what you feel from 1 to 10. And this is called the patient questionnaire. We will use BCA. We will use diffusion-weighted MRI. We will use patient history. We'll use environmental sensor to come with a precise diagnosis, because the main or the good thing about prostate cancer, if you detect it early when it is still in the prostate, the treatment 100%. The treatment 100%. But if it is tried to get out of the prostate, the patient usually their survival rate for 5 years around 25%. So this is one of the project, and I did this because of my advisor. Then and again, this is another project that we are working on it, and we have paper. It will appear very soon in Nature in Medicine. This is we are using a stem cell in the treatment to treat the people who has heart attack. So my role in this project is to evaluate the outcome of stem cell. So we are using 4-dimension MRI, we call it cine images. We use dynamic contrast MRI. This is traditional MRI, but we are using gadolinium as a dye on it. And the third one, we're using tagging MRI to measure how elastic the heart. Then after we put the stem cell therapy, or after using the stem cell therapy, I have to quantify the performance of the heart before and after. And in this system, we have the first one here, Dr. Robert Booley. He's the editor of Circulation Journal. This is journal, its impact factor around 18. And this is the best journal in the area of heart. And we got this day a new result, and we submitted to Nature in Medicine, and it got be accepted. So it will appear very soon. So I did this is because I grow in Egypt, especially in Delta, and in Delta region we have a lot of problem related to renal cancer. And in 2004 I started to work on this project, and the main idea we need, and when I met with one of pioneer in Egypt in this area is called Dr. Muhammad Ghunaim. He told me right now when we transplant a kidney, the only way to make diagnosis, we have to make a biopsy. And usually after the surgery, the patient didn't like to go to another surgery to make biopsy. This one thing. Second, we did biopsy when the patient didn't feel well. And at this stage, the patient lose more than 60% of the new transplanted kidney. So this is effect on the lifespan of the transplanted kidney. So he told me if we make something non-invasive, this one thing. Second, if it is, if it can detect the rejection early when the kidney started to become abnormal by 10% or 20%, we can increase the lifespan of the transplanted kidney. So I start work on this project in 2004 with him, and we continue till now. And we develop, this is based on using dynamic contrast enhanced DCMRI and diffusion weighted MRI. And we did blind study with University of Michigan. And when we did blind studies, this technology able to, so far, to classify 29 patients to correct out of 30. And this is completely double blind. We didn't see the patient, they just send us the data, we make analysis, and they send it back to University of Michigan, and University of Michigan, they compare it with the biopsy. Why we selected University of Michigan? Because University of Michigan, they have called biopsy protocol. The people go, even they suffer from something or not, they will go and every 6 months to make a biopsy. And we selected them for this reason, to see if someone come with no reason, he doesn't have any problem, and our technology able to detect, no, he has a problem in his kidney, but still at early stage, and to confirm it by biopsy. This is confirmed, this technology can be used for early diagnosis of acute renal rejection. And after we did this project has been funded by NIH, National Institute of Health. And this is another project, and we started to collaborate here. In this project, we are collaborating with Cleveland Clinic at United Arab Emirates, University of Mansoura, and University of Louisville. And the main idea here is the people who are diagnosed are diabetic. Everyone knows that diabetic or the people who become diabetic after some reason, after some time, they affect their vision. So we develop a technology that we can use OCT that can check the anatomy of the retina, and OCTA to check the vascular system of the retina, and develop accurate technology for early diagnosis of retinal disease. And when we publish our work, they selected this because we are the pioneer in this work. They put it in the cover of Medical Physics Journal. This is one of the technical journal in AI, and the idea of this work has been published in JAMA, and the JAMA is one of the pioneer journal in it is similar to Nature, and we publish it as in 2018. I think Dr. Isa, when he visited Louisville, he go and he sees the center with us, the center of spinal cord, and he saw the patient. And this is a very big project. And we are working with Dr. Susan Harkima, which is the director of this project, to help the people who has a spinal cord injury in the age between 7 years old, I think, until 25 or 27, to help them to start to make the basic large movement. And I just run this video to see.
Cox is paralyzed from the chest down.
Did you hear the voice?
He can't move even.
Yes, it has a voice. It has a voice, yes.
But doctors implanted this device, sending electrical stimulation to his spine. And when Dustin turns it on, oh, there you go. Yes. Oh my gosh, he can move on demand. Okay, right leg back. And then forward. That's amazing. Yeah. When the stimulator's turned off, Dustin can't even sit up because his torso muscles don't work. But turn it on, and Dustin can sit up without any support at all. The first time I turned it on, it was exciting and emotional for me at the same time. Emotional because I was told that I'd never be able to walk or move my legs again. Dustin is one of 4 patients in a new study published Tuesday. Despite their gains, none can walk on their own. The device works by activating one leg at a time. It's not the first time electrical stimulation has helped paralyzed patients, but experts say this technique may become an important tool in the toolbox.
I think that what's incredibly exciting is that we've opened up a realm of possibilities of what we can do now with people who are paralyzed, and we've just scratched the surface.
Elizabeth Cohen, CNN, New York.
Okay. So my role in this project, again, this is after we make up the device that we implant by neurosurgeon, we need to make program. And now it comes to the idea to personalized medicine. We find there is no one programming fit all the patient. Every patient has its programming way. So some patient, for example, they have to send the signal to them 0 and 5 volt. Some patient, we have to make it -5 and 5. Some patient, it will be -5 and 0. Some patient -1 and 2. So the level of the voltage different. Also the frequency. Some patient respond start from 5 hertz. Some patient need to go up 7 or 8. Some patient, they start work at 4 hertz or 3 hertz. And the combination, this device has 21 terminal. So not the same terminal will work for all patients. The combination is different. So usually we take from 4 to 6 months to make a complete programming to this device. My role to them, I stand with them and I get the signal by using EMG sensors. And as the muscle contracted, I visualize in front of them. If it is blue, this is little bit contraction. If it is red, this is called strong contraction. So during the clinical guy started to put different combination, he looked to the screen. As it become red, he starts, this is the contraction that he's looking. And when he sees blue, it start to respond. So this is mean to him, to guide him, he's in the right way. Right now, we try to use the same idea for bladder. But it is the opposite. For bladder, we need to help the patient who has a spinal cord injury to help them to charge the bladder. And when they go to the restroom, they push in the bottom to make the bladder's contraction. Then they can make discharge. After this, we are not stopping here. But after this, because this is people, they move very little. So we try to help them in physical therapy. So because their muscle start to die with the time. So what we are trying to do is every 6 months we make MRI in their muscle. Then we can quantify the ratio between fat and the muscles. If the ratio is still the same, this means the course of the physical therapy fine. If no, the ratio fat to muscle start to increase, this mean the course of physical therapy now is not enough. They has to increase the period, or they can start to increase another type of exercise in the physical therapy. So this is just to give you some idea of my lab, but I will go a little bit in details in one of the projects that I like it, and we have many universities to collaborate with. This is one in big data. And I started, and this is an example for personalized medicine. To the people start to understand what we mean by personalized medicine. I started this project in 2004 with professor from University of Johns Hopkins. His name is Manuel Casanova. He visited our lab and gave us a presentation about autism. To be honest with you, at this time, I didn't know even what is autism in 2004. So my first question to him, what is autism? So he started to tell me this is some mental disorder that affects the children, and they make some problem for them in communication with the other. This one sense also they can affect their activities. So I start. So this is again, this is a brain disorder. He said yes. And what I told him, what is the current way to diagnose it? He told me, no, the parent must stay until their child become like 3 years old or 4 years old. They start to see this is his or their children has a problem to talk, has a problem to have eye-to-eye contact. They start to take him to the doctor, and the doctor start to make diagnosis. The main problem, this is type of diagnosis very, very subjective, and they depend on the experience of physician. So I told them, okay, is this a big problem? And again, we reach the point that we need the people from commercialization come and sit with us, especially when we go to NIH and we have grants. The first question is, this is a big problem? Because if this is problem affect half % or 25, or 1% from the population, this is not will be high priority, especially if you take money from federal agents to support this problem. If you will go to investors, the investor must feel this is important problem. Then the people from commercialization team come with this statistics to us. 5% of the children in US high risk for autism. This one thing. Second, they told us 1 out of every 68 children born in US suffer from autism. We start now. Then they give us some number about how much US spend in autism. In 2006, they spent around $40 billion. In 2012, US spent $120 billion. In 2018, they spent $360 billion. So this is a big market. So this is they told us, and out of 360 million, 35 billion only for diagnosis, because this is number for diagnosis and treatment. Out of 360, 35 billion for diagnosis only. Then, as I told you, we asked him, what is the current way to make diagnosis? He told me this is how they start. The parent starts, there is something wrong with their children. Then after they start to feel this is problem, they take to the doctor. After they take the doctor, by the way, he can't make from one session, especially for autism a diagnosis. He will come and schedule several meetings, and the meeting with the parent and with the children to keep asking them some question. This is take around from 66 to 18 months. Then, just 1 minute here. Then after it, he to go to the doctor will analyze the visit and the discussion with the parent and his discussion with the children. Then he maybe say, okay, can you make MRI for us to confirm his diagnosis? Then after he makes the MRI, they say, okay, I think your child may be autistic. And they make final diagnosis. This take around from 2 to 3 years. So another problem for autism, that the autism is a spectrum. It starts with this is the border speech delay. This is the border between autistic and control. And by the way, speech delay not come only for autism. It can come from several other reasons. But one reason of them is the autism. Second, maybe they have problem to pronounce some word. Also, they have some problem to interact with his friend, with his parent or her parent. So this is, so as we go from the border of control until we reach the severe autism. The severe autism is they have the student doesn't not the student, the child doesn't move at all, doesn't talk, his behavior is very bad, his interaction with the people around him is very strange. This is what is called autism or severe autism. So it is a spectrum, and some of them overlap with the other disorder. So the question is, can we develop something objective and also early? So now we have to challenge objective diagnosis and early diagnosis. So this is why we start the concept called the big data in autism. One of the input to us will be the behavior report, and we can use this behavior report as the ground truth. After 4 years or 5 years, we can compare our diagnosis with the report that come from 5 experts. This will be our ground truth. Imaging marker, we're gonna use 3 types of imaging: structure MRI, function MRI, DTI. And we're gonna use genome for the patient, and we're gonna use family history, if this is history has any history of brain disorder. And again, this will be our ground truth or our validation. So NIH make very good study, is that they will start to collect data from high-risk family, and the high-risk family is the family that they have one or more cases in the family diagnosed are autistic, and they asked them for after 3 months from delivery, they go and they make all this type, genome, MRI, structure MRI, DTI, function MRI, and they ask the researcher start to work on it, and they keep, and after 4 years, the NIH will get the diagnosis from 5 experts. And they didn't share this diagnosis with the researcher. And they need the researcher in double-blind way compare their accuracy with the diagnostic accuracy that is confirmed after 3 to 4 years from the delivery. So this is our system. We try to make it, this is the artificial system that we use. One of the input will be structure MRI, DTI, fMRI, genome data, and the behavior, which is the validation. We make a fusion, then we make a diagnosis. So, and again, this is the way that they make a diagnosis, and they told us this is very subjective, and but NIH, they try to do at late age and by 5 experts. And Dr. Casanova, it is just based, they ask the child some question, ask the parent some question, and after 5 to 6 sessions, they come with a conclusion, this is child is autistic or not. So now, this is Dr. Casanova, when he come to the lab, okay, what is your idea? At this time, Dr. Casanova work at post-mortem bank. And post-mortem bank, at this time, we have around 40 to 50 autistic subjects. After they born, they donate their body to this bank. And we take brain tissue from this post-mortem patient. And this is what we see. This is some pathology images. Dr. Casanova come and they see that the one on the right is autistic subject, the one on the left is control. We find that the autistic subject, they have many neurons in the brain, and compared with the control subject. At this time, he asked us, can you make analysis? We make analysis by dividing this is images to vertical column, we call it mini column, and we end with this conclusion. The thickness of this mini column in autistic thinner than control, but they are many. They have many neurons or mini column in this. And this is support the theory that autistic brain is big. So if you Google the internet and search for a big brain is the autism in terms of the volume. Based on this, we start to work with him, and we're gonna use to measure the brain size, we're gonna use structure MRI because it gives us the anatomy. So I can measure the volume. Then I can measure the brain functionality, which is related to the behavior, by function MRI. Then we can measure the brain connectivity by using DTI. So after we did this, we start to measure the brain volume, and we can make a diagnosis. So for structure MRI, in order to measure the volume, we have to extract the brain. And we worked in this area for 3 years, but we didn't end with good result. And when we make analysis, we find there is another parameters affect the brain volume. One of them is the age. Second one is sex, if this is male or female. Also the pre-processing. So we say, we need some other metrics that less sensitive to the age, less sensitive to the sex, and less sensitive to the pre-processing. And we're gonna use what is called shape descriptor or morphology descriptor or anatomy descriptor. And this is what we did in this. We take the images. After I take the MRI image, I extract the brain. And after we extract the brain, we will measure the curvature or the differentiation on the surface of the brain. And we find this in my team work on this idea, and In 2013, there is a competition in Japan, and my team participated in this competition, and our approach is was the most accurate approach, is generate around 96%. But even if it was the fast, it is the most precise, but also is the fast. If you compare our approach with other, our is 6 seconds. The other takes 3 minutes, 35 minutes, and 2 hours. And someone say, why you care about the speed? Because you will put this software in the hospital, and you have to make it fast because the doctors are busy. They will not stay the result from the software 5 minutes or 10 minutes. So this is some constraints on the people who work in to develop a product. So again, after we extract the brain, we measure the curvature, which is similar to differentiation on the surface, and we start to make diagnosis. So based on this, we start to divide the brain to areas. It's called Brodmann area. 100, it is 50 area in each loop, because the brain is 2 loops, and we get this as feature from it, and we integrate and we make diagnosis. And after we tested this system in many data sets, the first one, national database for autism research called NDAR. They have around 200 subjects, 135 autistic, 65 control. Their age was around 23 months. At this time, when I get the funding from NIH, was my technology, control and autistic. After we got this result, we go to NIH, we present our data. They told us this is great, but this is not enough for the doctor. The doctor will never accept that you give us black box, and they told us autistic and the control. If you told the control, you have to tell us why. If it is autistic, you have to tell us why. So in this case, we started to discuss how we can help them. Again, the accuracy was around 94% on this database. And this is how the second grant, they give us second grant to help them to visually why not. So in this case, we started to divide the brain to areas, and if the area is abnormal, I show it in red. If it is match the control, I show it is in blue. If it is in border between autistic and control, we show it in yellow. They told us, great, but this is not the best way for the physician to take a look. This is too much number for us. You have to come with another smart way to save the physician time. In this case, we come with this idea. I take this number and I put it in color in the brain. So in this case, the doctor will see the anatomy, and from the color, he say it match. If it is red or orange, this is mean it is match autistic. If it is green or blue, it is close to control. If it is in yellow, this is mean it is borderline. And in this case, from the anatomy, he can detect which area is abnormal, and this can correlate with what he sees with the patient. If this is area related to memory, he can check the patient memory. And yes, if it is match, this is mean correct diagnosis. If it doesn't match, there is a problem in our technology. And this is what we started to do. What is even clear, even the control subject, they have some area match with the autistic subject. And also in autistic subject, not all the area in the brain are autism. Some of them are match control. And this is supports the idea or the theory that autism is spectrum, is not 1 degree of disorder. And second validations, because by the way, this technology has been licensed by a company in New York. They asked us to start to test our system in data collected from multi-center. So we got some data from Yale, Stanford, UCLA, and Carnegie Mellon, and we started and we sent the result, the accuracy of our system in each site, because this is another step to get FDA approval to test your data on that collected from multi-center. Third approach now to get FDA to now test our approach in data collected from different countries. So right now we are working to get some data from China and the Middle East. And the accuracy here was around, the average accuracy of all across all the sites is around 90%. For function MRI, this is the second component that when we ask the patient to do a certain task, if it is controlled, he make it on time. But for the subject is autistic, we find a problem in synchronization between left hemisphere and right hemisphere. And this is why we started this is approach to get the data, then we can measure the signals that come from the brain, we call the bold signal, and we start to measure the synchronization between left hemisphere and right hemisphere. When we did this, we speak that autistic subjects within the hemisphere are over-connected, like short circuit, if I talk in electrical engineering. If across the two hemispheres, it is under-connected. The control we call perfect connected. So we did this and we follow the same system. We take all the same areas and we've used together and we use the same system of visualization and we tested in many data sets. The first one is called NDAR, National Database of Autism Research, and the accuracy here is around 96%. And this we use the same way to visualize. And again, if it is red, it's close to, this means this is area is autistic. If it is below or close to below, it is match control. If it is yellow, this is in borderline. The last modality was data eye, and this is to measure the connectivity. And this is what we see by our eyes in the pathology images. So we get, and this is Dr. Casanova, the way to interpret this. Some autistic subjects, they put their hand in very hot surface and they didn't remove their hand. Or they have a knife and they cut their skin and they didn't stop. Did they feel it? Yes, they feel it. But the main problem that the signal, his idea that there is no direction to the signal go from cortex to the deep structure, like this signal didn't add up to reach a certain threshold that the brain send a signal of decision, stop. No, the signal, it is not add up. Why? Because this is his way of interpret the result. In control subject, the way that our neurons look like ellipse. So we have directions. But in autistic, they have many neurons, but they take a shape of circle. And the circle, we didn't have dominant diameter. So the signal go in all directions by the same strength. Based on this, he claimed that the signal never add up in autistic subject to take a decision to remove his hand from the surface, to stop cutting his hand, and all the stuff. And we did this, and we use John Hopkins because DTI doesn't quantify the cortex, it quantifies the deep structure. We did the system, we use John Hopkins, the Atlas, and we got accuracy around 86% and around 100 subjects. 50% is autism and 50% was control. And now the question is, and also we use the same way to visualize the data. So now we finalize 3 modalities. Now, what about fusion? We go and check our data and we start to integrate all of them together. When we integrated all of them together, we find that we have 50 subjects have the 3 modalities. After we get the modality across using the three modality was 97%. And for fMRI alone was 96, and DTI is 96, and the structure MRI 97, and the overall was 98. Someone can say, okay, do you see difference between 98 and the 97 and the 96? No, the question no. But we didn't do this is to get little bit improve in the accuracy. No, we did it to get final understanding for the case of each patient, because when we get a comprehensive report about anatomy, about functionality, about connectivity, this is will help the doctor to decide the best treatment to the patient. So when we fuse them, we didn't looking to improve the accuracy. If it is improve the accuracy, that's great. But the main idea to understand each case in more detail to specify the best treatment. Then genome data. Genome data now it come to validate our results. So we get all this data. We get the NIH provide us with the genome data for all subjects. We divided the autistic subject to 3 groups based on their severity, and we start to make a correlation between genome. We find many correlated, but what is good when we did it, we find some genome that is already reported in the literature, and I mean by literature in Science and Nature, that some of this genome correlated or reported that is related to neurodegeneration. Neurodegeneration, this is now validate that autism, it is a disorder come from anatomy, because there is some theories say autistic, it is not pathology disease. This is come from the environment. The people claim that everyone born correct, but based on the environment, it can affect his way and change from control to autistic. But this is the result confirmed. No, what some genome we find it is correlated with neurodegeneration genome that is reported in literature, and this is what we investigating right now to make it with more data sets. So what is next? So what is next right now? My team, this is what we are doing right now in my lab. And I think by end of this year, we can get the result to finalize the whole system. We get the patient, I will get all function MRI, DTI, fMRI, and DTI, and genome. I will make the diagnosis. And after I make diagnosis, I will map it where it is in the spectrum. In this case, we reach the point that we able to make personalized diagnosis for autistic subject. Again, for sure, I am not the one who did all this work. I just started this work. But as I told you, we have many teams behind this work. A student, our medical collaborator, our commercialization people. And this is, again, we started this project in 2004, and we still working on it till now. Also, I like to thank all lab member and all people at University of Louisville, including the president and my dean and the vice president of research, because if you didn't get the support from your university, you will not able to do such work. Also, I like to thank all my friends and all my collaborators, starting from Dr. Isa Bastaki, that I am so happy that I hosted him here in Louisville, and we spent a couple of days together. And again, my feeling is a great leader, and I'm sure that he will make a big difference at University of Dubai. Dr. Shal from UMass, Dr. Suzuki from University of Chicago, Dr. Casanova right now in South Carolina, Dr. Henry Kaplan, UCLA, Dr. Dick from University of Pittsburgh, Dr. Muhammad Ghazal from Abu Dhabi, Dr. Noval from Khalifa University, Dr. Fatma from Zayed University, Dr. Gimel Farb, and this is guy, again, he's my advisor, or I consider him as my real advisor from University of Auckland, and Dr. Muhammad Abul Ghar from Mansoura University. So again, I am so sorry because I take too long, but I like to thank everyone for his listening. And again, I will be so happy to answer any of your questions if I know.
Thank you very much, Professor Ayman, for this outstanding presentation. Now, before I open the floor to questions, I would like to say that, like, you know, when we talk about big data, we talk about data science. And I'm giving the good news that University of Dubai now is offering Master of Data Science, starting from January. So this is a good news for everybody in UAE because, you know, University of Dubai is always distinguished by their high quality of education, thanks to Dr. Isa El-Bastaki. So I maybe start with Dr. Isa, if you kindly give your comments or question, please.
Well, first of all, thank you very much, Dr. Ayman, for this really fantastic presentation. I was in the middle of the presentation. I said I have to call my brother to come in because this is something important for him. He didn't listen to all of it, but I think he may have some questions. I don't know. One of the things that I tell everybody, medicine is Greek to me. I don't understand medicine, but I know the technical side of it when it goes to technically. I can't ask any question because I'm not an expert in it. But one of the things is I think when you talk about big data, you're talking about buying 1 terabyte from Google just to do one project. So you can see how big the data is becoming. And I think when University of Dubai working with starting the master's degree in data sciences, I think it's a good thing because it has big data, it has analysis, it has artificial intelligence, and all these plus security. I think technology is helping the medicine, and I think Dr. Hassan Nashash is also here. He could have any question, but I really like to thank you very much. One of the things I want to do is now we have, you know, a meeting of scientists every month. Last month we didn't meet. Maybe this month we'll meet on the 31st of October. Is it possible for Dr. Ayman to do it again for the scientists?
No problem. That's fine. That's fine. And maybe I will put another disease because maybe I can put also the kidney one because this kidney one is another type of personalized medicine that we are doing right now.
Okay.
For sure.
Thank you very much.
Thank you, Dr. Isa. Professor Hussein, kindly, if you may have some comments or questions.
Yeah, thank you very much, Professor Ayman. It was an interesting seminar, and I would like to ask you something about, you know, the new device called the Butterfly IQ. I don't know if you heard of this, which is ultrasound device which can be connected to the iPhone. And do you think this will change the way, because it means that, you know, like while I am at my home, you know, like my doctor can examine me, and this will be again another way of.
This is, yes, this is a very good point, and we started to discuss some idea like this is especially for diabetic people, for example, because ultrasound is still very good, for example, for cardiac. So especially the first, anyone has any cardiac problem, the first step he do is ultrasound. For pregnant also the first choice or the most safe choice, it will be ultrasound. So for sure for some diseases it will help, and right now we start, I have a project similar to this for diabetic people who has some wound. So right now we need, instead of going with the doctor every day, we need to put some smart thing in their cell phones. They can take a picture to the wound, send it to the doctor. The doctor, he can quantify it is healing or not healing. The same we can do with ultrasound. If someone has any heart problem, he can send even some data to cloud system, and when this cloud system start to feel there is something abnormal, he can send him alert and send it to his doctor alert. Please call him because there is something abnormal. We try to do this even for the people who has a spinal cord injury. We find that our device that we give to them increase the blood pressure. So we need now something to, when they start to walk, if their blood pressure start to increase, they alert them, please take a rest. Because right now, your blood pressure increasing. If they didn't listen, after a certain point, we can call 911 because the blood pressure increasing, so it can make a big damage. So yes, for sure, this is portable medical devices that can be connected to the cell phone or something like this. It can improve the health care and help also in the area of personalized medicine.
If I may ask you another question, I have seen that, you know, like Siemens now, they are using ultrasound for monitoring the COVID patient, because as you know, if you are on a ventilator, it would be very difficult to move you from your bed to the CT scan or the MRI. I'd just like to hear your views about using ultrasound.
Again, I am working on COVID. I am working on COVID. This can help also to monitor, as I mentioned, the heart, because ultrasound, it is not the good modality for the lung, because the lung contain a lot of air. So in ultrasound for the lung will be noisy, but they check the heart, because as I told you, the response of COVID-19 affects the patient, and this is what I see right now in Norton Hospital here. Some people, COVID-19 affects their heart and the kidney. So this can help in this case. If someone COVID-19 start to affect his heart and will cause heart failure, it will help a lot. But for lung, the best way right now, we are using X-ray. If it has become complicated, we use CT. And by the way, I want to mention University of Louisville, one of the sites, they are selecting it to test American vaccine right now. And I have right now data from 300 patients. They have everything about them. And also we study the response to the new vaccine.
By the way, what was the initial results of the vaccine?
So far, I can tell you we have around 50 patients in Louisville. So far, the result is moved very, very well. This is what I can say. Very well, and I'm participating in this project, and I'm analyzing their data, everything. We didn't have anyone got infected from this vaccine so far. And we have weekly meeting every Sunday at 10 a.m. to discuss the result, and they share it with me, and I make analysis to them. So far, everything moves in the right way, so far.
Thank you very much, Professor Ayman.
Thank you, Professor Hussein. Professor Hassan Nashas, may you kindly give your comments, or if you have a question, please.
Yes, thank you, Athik. Thank you, Dr. Ayman, for a very interesting presentation, and also nice, meeting you. I listened to all the interesting projects, and I noticed at the beginning of your presentation, you mentioned something about your involvement in projects related to COVID-19. Yes. Can you elaborate a little bit more on what what is the project is about, and what are the objectives of the project, and how far did you reach so far?
Yes. I started in this project because when we started COVID-19, I got a call from infectious disease at University of Louisville, who right now work with Pfizer to test the new vaccine, that right now there is no objective way to decide who will put him under to use a ventilator or not. And the number of ventilator is very, very limited. So they share with me data. They bring data from China, data from Egypt, data from USA, and they share with me the people who got infected by COVID-19 and they didn't need a ventilator, and the people who has to put them in a ventilator. And I started now to study their X-ray and CT, and I started to follow their pattern, the pattern of infection, to see if the pattern of the infection inside the lung, fit or match the severity of the COVID-19, then we can say this is must need to be ventilator. So I got from each patient 2 CT scan. The difference between each 2 scan is from 2 to 3 days, and I get also the all blood markers from them, or the blood test, and I started to to train, to develop some new imaging marker to capture the infected region in the CT or X-ray, and I use the pattern, the shape, the area of this region as input to my artificial intelligence, and we got it in result around 94%, and we submitted this result right now to Nature scientific report, which is published by Nature, and I think since 2 months ago. And this is project also I need to mention, it has been funded by Egyptian government.
Thank you. I have another question related to the chemotherapy project that you mentioned earlier. And what's the practice? I mean, before your involvement and the results of your project, what was the practice in medicine to decide when to stop chemotherapy?
Until now, yes. No, until now there is no. This is why you have to meet with the physician first. The physician come to us and they say, Ayman, until now there is no markers that the doctor can use it to stop the chemotherapy. This is depend on when the doctor says the patient is suffering now from breathing, so it depends on the experience of the patient, of the doctor. So this is why he come and they say we need to develop something objective, and it doesn't need doctor experience to decide. So I told him, okay, but usually what you are doing? He told me there is a ventilation device. He tried to use the numbers that come from it, and if he sees that the ventilation become it is not high, and he feels the patient is a little bit sick from the chemotherapy, he decided to stop it and start the type of therapy called nuclear therapy. So, but he told me this is not correct for all patients, because some patient maybe he has some infection like influenza or something. So he get tired from this is influenza, especially the people who got chemotherapy, they have very high risk to infection from common cold, from influenza, and from all this stuff. So he told me this is not he believes this is not the best way. So he need a marker that come from the tissue. And based on this we contacted Siemens, and the Siemens developed for us 4-dimensional CT. 4-dimensional CT to able to capture how the lung is moving. And from this movement, I can measure exactly is the lung tissue in all the places still elastic or not? This one question. If it is not, which places is affected? Then the doctor can say, this is still not important. The most important for me is this. Then the doctor can be balanced between the outcome of chemotherapy and the outcome to keep the lung working.
All right. Thank you very much. Thank you, Doctor.
Okay, Dr. Hassan, thank you very much. Dr. Yusuf, kindly, if you have comments, I know you are the physician. You are the only physician among us. I'm not sure that if you can hear us, Dr. Yusuf.
I can hear you. Can you hear me as well?
Yes, Dr. Yusuf.
Yeah.
Yes.
Yeah, but I came in late. Dr. Isa just called me, and I was downstairs, and I just arrived, so I missed a lot of what was said. It was what I heard was for me, this was quite interesting. One in which you, as Dr. Baz explained, he put a lot of things together in order to be able to diagnose autism. Now what we do is we depend mostly on the examination and the signs of development. We call them development signs, where people, there are milestones where children develop certain qualities, and so that's what we depend on, when we make the diagnosis. And as he said, it's usually by 18 months and 2 years, we have made a diagnosis. But there are some that do not have the diagnosis until they're adults, even adults. So this would be helpful. I mean, in those children. Yes, and I see the figures that was given was quite impressive. I mean, the sensitivity data and so on was quite impressive in the 90s, which is really quite impressive with regards to the diagnostic test. He also said that he puts the genomic data as well into the pile that he does and puts all of these together, and that's how he gets it. The genomic data is quite huge. And you have to pick only those that are relevant to the particular problem before you put them into the pile and make the diagnosis. This mapping of the behaviors and so on has been done lots of time previously. But what I heard is that these things are all put together in order to make the diagnosis. And I think it's very good that it's going to be very helpful if it works. I haven't seen something work, so I really can't make any comments on this. The only comments I can make is on the clinical side of things. The other thing that I have some knowledge about is the COVID-19 infection and the pandemic that he was talking about, and see the lung movements and so on, and get them all together. With regards to the vaccine, I am a little bit skeptical about the way in which this is done. It's too soon, because there are certain steps and phases of tests that you go through, and that takes a very long time. What we are doing now is actually cutting it short, so we don't find the chronic effects, the long-term effects of the vaccine, and so on. And I'm a bit worried about that, and that they're putting it into the market so quickly without actually doing the tests that we used to in the past. Any drugs or vaccines or anything have to go through this process so that we find out. And so I'm a bit skeptical about this. And we've, in the UAE, you probably have heard that we have introduced now 2 vaccines. One, the Chinese one, and the other was the Russian one, what's called the Russian Sputnik or something. And they're both different. They work differently. One is a vector, which uses a virus as a vector to take the protein into the body, and the other is just a protein. It's not a live vaccine. So you must have heard about the Johnson & Johnson one, where they find there was a problem, a neurological problem with one of the patients.
Yes, stupid, yes.
And yes, and so the US one, I haven't heard of any still side effects from that vaccine, but it's still early days, and we have to let the process go before we actually judge on what it is. I don't know what Dr. El-Baz thinks about this.
I completely agree with you. This is why I am telling you, no one in US will take responsibility to say this vaccine is good or not without evidence. This is why, for example, even in Louisville, we are testing the one by Pfizer. I think the one by Pfizer, this is the one by this is the one that try to marketing it in US. We try to collect the data, but I think no one will take the risk to say this is safe and they put it in the market and without completely testing it, because in US it can cause a lot of problem to the company. But so far, this is what I say. So far in our site, we tested 50, everything running. So far in the Pfizer one, moving without problem. But as soon we find a problem, we have to stop it and report to Pfizer, because it's a contract between Pfizer and the infectious disease in lower. This is completely agree with you. For genome, I completely agree with you. This is why in my talk, we try to get the genome that related to neurodegeneration, not all the genome. And this is the one we try to find a correlation between them and our imaging marker. And what we found is some of them show correlation between the imaging markers that come from DTI, from function MRI, from structure MRI. So what I can say for COVID-19, and I am very robust about it, our software that it helps the doctor that can determine which patient need to put him under a ventilator device and which patient is fine and he didn't need this. Because I keep taking the imaging from the lung and I start to analyze the pattern of the infections, and at a certain point we have to say, yes, this is a severe pattern, you have to put him under ventilator. The pattern here is not severe and the patient can survive without ventilator. Yes, this is the result. I can admit it, and I can see we tested right now more than 200 subjects, and we got from Norton Hospital this is week another 300, and we got from Egypt another 200. So in coming 2 weeks, we're gonna test the software in around 500 patients again.
Okay, thank you, Dr. Yusuf. Dr. Ayman, I have a question to you, please. You know that we have two approaches as for us as an engineer when we deal with the biological species. One of them is invasive approach, and the other one is non-invasive approach.
Yes.
And actually, we are doing very well in non-invasive approach because that will have, good for the patient. So to avoid him to go to this device to be inserted in his body, like medical imaging, ultrasound, these kind of things. So still, the invasive approach still exists. My question is about Neuralink. You know, Neuralink being announced by Elon Musk recently, and that is goes to the invasive approach because the device has to be fixed in the skull of the human. So my question to you: what kind of challenges for us as engineers to get these electrical signals that deeply from the brain that to avoid such an invasive approach?
I can tell you again, the main problem, again, to determine which approach you have to follow, invasive or non-invasive, this is not engineering decision. This is come from the physician. For example, when Dr. Yusuf has a problem, he believes that it can be solved in a certain way. Because at the end, I have to do what my customer believe it will work fine. So, for example, this is why when I present my research, I have at least 1 or 2 physicians sitting in my team. And because again, what he need, because this is the one who you're gonna use your technology. So this one thing. Second, when we talk about the sensor, because I work in little bit about it, the main problem that when you put the sensor on the skull from outside, you get what is called a surface signal, but you didn't know where it is generated. I need to know the origin of generation this signal, because when I know the location exactly in the brain, you can start to put your sensor and you can start to put something to help the patient, for example, to memorize, to help them to walk, and this. So it depends on the problem. It is not an optional. So far the current technology to put the sensor on the surface, it works in some application, but not in all applications. Some application you have to put the sensor inside the brain, and this is must done by the neurosurgeon. and he implants the sensors and he can use it. So it depends on the, again, so far, and this is why, for example, the EG signal, if we see the EG signal, we get it from outside.
Correct.
Then people say this is surface signal and I didn't know where it is generated. So we start with the functional MRI. The functional MRI, it helped me to know the location of it, but now I know. So if I need now to measure it real time, I have to go and put the sensor inside. So far, it is not an optional. It depends on the problem that you need to solve and the solution that the physician will trust it and will help you to get FDA approval for it. And by the way, this is very important. When I have a technology, before I go to FDA, I have to present in front of physician. And the physician from the concept must believe this is the best approach. Then we go to the testing. But even the physician say, no, I didn't believe this will work with all patients, and give you some example, we will not even go to the testing. To make clinical trial 1 or clinical trial 2 or clinical trial 3 to get FDA approval for my technology. So who decides? This is not an option for engineer. This is decision come from the physician.
Okay, thank you.
By the way, Dr. Fatma is here also. Dr. Fatma.
Yeah, I just saw here.
Dr. Fatma, you want to say something?
السلام عليكم، كيف حالك دكتور أيمن؟
ازيك دكتورة فاطمة، أخبار حضرتك إيه؟
الحمد لله، كيف حالك دكتور؟ Thank you very much for your time and effort. I joined late, but I know the quality of your presentation always very high,
I just
mashallah.
need to mention Dr. Isa, Dr. Fatima got her first patent already approved last October. So this is her first patent. So, and
thank you, Doctor.
I can tell you by, for example, when I have a patent, usually take from 2 to 5 years to be approved. Dr. Fatima, her patent is the fastest patent I saw. She take it in 1 year.
Congratulations, Dr. Fatima.
Congratulations.
Even when I got the letter from the patent office in USA, I didn't believe. We just submitted last October. So how it come? Did they have a problem? They did return it back to us. Then I asked my assistant, please, can you go and check if this is truly approved? She go and say it is approved. All the claims are accepted. Yes, all claims are accepted. Then I contacted Dr. Fatima. Do you know that your patent has been approved? At this time, she didn't know.
Yeah, alhamdulillah, Doctor. Mubarakah.
This is good news. Again, I can tell you, this is the fastest patent I saw. I tell you, all my patent take from 2 to 5 years.
We say على نياتكم ترزقون, and she is a very kind person. That's why she got it quickly.
Thank you, Dr. Ayman, also for your effort. والله تعلمت a lot from you. يعني he's my mentor صراحة.
But I like maybe to say something regarding the collaboration between University of Dubai and University of Louisville. We have MOU signed earlier. Now we're working on 2+2. So students who come to University of Dubai, they take the first 2 years of engineering, and then they continue in Louisville to finish the bioengineering. And this is already a pre-med. So they need 3 more years to become a medical doctor. And I think this is very good. So in 7 years, with the bachelor's degree, they can get the medical doctor. So I think
it's approved, Doctor. From
we are working on it. Yeah, we finished nearly. Approved from their side. From us, we don't need approval because we don't give the degree.
Oh.
Just take 2 years and they go there.
We just waiting for Dr. Isa to sign the final contract or the final agreement.
Yeah.
Inshallah.
Inshallah.
So now we can do medical doctor degree in 7 years, not like before 10 years.
Yeah.
Which is very good.
Okay. We don't have any more questions. So in conclusion, we would like to thank Professor Ayman for his outstanding presentation, and hopefully we can invite you more in the future, inshallah. Thank you very much.
Yes, I am ready anytime you want me to give a presentation. I am ready anytime.
Okay, thank you very much. I think the doctors need to listen from beginning. They didn't see also. Next time with the scientists together, please, we'll go for presentation.
And maybe next time also we're gonna present this. We have a very good project about predicting the response of chemotherapy for bladder cancer. So in this case, we can tell the patient in advance if you're gonna respond to chemotherapy or not. Then to make this will be his decision. This is something that we did it using multi-input data and also show very good result. And we did this collaboration with Kidney Center in Egypt.
Very good.
Okay, thank you very much.
Thank you, Dr. Wasik. Thank you, Dr. Isa.
Thank you very much, Dr. Ayman.
Thank you, Dr. Hussein. Thank you, Dr. Fatma. Thank you, Dr. Yusuf. And thank you, Dr. Hassan.
Thank you very much.
Thank you.
Thank you.
Have a nice night.
Thank you to the audience, all of you. Thank you for joining.
You still have the day, whole day, Dr. Ayman. Send our greeting to your postdoc in the lab or doctors.
Thank you so much. Thank you.
Thank you.
Thank you.